Hello everyone. This is lecture 4.5 of the GPU teaching kit. We're going to be presenting how we can handle arbitrary matrix sizes in tiled algorithms. The objective of this lecture is to learn how to handle arbitrary matrix sizes in tiled algorithms. And we're going to learn how to do boundary checking when loading tiles, and we're going to learn how to regularize the contents of tiles to simplify the core computation. And then we're going to extend our techniques to handling rectangular matrices. In the next few slides, we're going to illustrate the problems with tiled matrix multiplication when handling matrices whose dimensions are not multiples of the tile width. This slide shows the phase 1 load for block 0, 0 for a 3x3 example. The reason why we're not showing phase 0 is that the phase 0 tiles are completely within the valid range of both M and N, and you should verify that independently. However, when we move to phase 1, we're seeing that for loading the M tile, we're going to be attempting to load 2 M elements in this example that are not valid. So thread 01 and thread 11 in this case need some special treatment when we load M tile. Even though conceptually these two threads are loading invalid or non-existing elements of M, in reality, because of the row major layout, these threads are going to be incorrectly loading the next elements, which are M10 and M20 in this case, into their shared memory locations. These incorrectly loaded elements are going to cause incorrect computation result if we use them in the calculation of the inner product for those P elements. Now let's turn our attention to the loading of the N tile. The loading of the N tile in this phase will involve thread 10 and thread 11 trying to load non-existing N elements. And this is a little bit different from the M case because those non-existing N elements are going to be totally outside the valid range of the N data. So in most hardware, this may cause a memory access violation because the program is trying to access a location that is not properly allocated. So that means that thread 10 and thread 11 need some special treatment, and we really should avoid doing any access to those locations at all. Once we have loaded the tiles into the shared memory, phase 1 of block 00 will consume the M and N elements from the shared memory, and this is just illustrated in this slide. So for iteration 0, the threads are going to be consuming valid M elements from the shared memory. So this is fine. However, when we move to iteration 1, all the threads are going to attempt to consume non-existing elements in the shared memory for both M and N in this case. So we need to make sure that none of these threads are going to contaminate their inner product value with these non-existing values. The previous example seems to suggest that the boundary condition of loading non-existing matrix elements only happen in phase 1 in the example or in the last phase of tiled algorithms in general. However, this is not true. Here we show the loads for block 1, in phase 0. And if we look at the bottom half of the picture, we see that thread 10 and thread 11 will be attempting to load non-existing M elements into the shared memory. And if we look at the upper half of the picture, we see that thread 01 and thread 11 will attempt to load non-existing N elements. So these threads will need to have special treatment in phase 0. So this suggests that the boundary condition checking needs to happen in every phase of the tiled algorithm. It's just that different threads in different thread blocks will likely have the boundary condition situation during these phases. To summarize, we see that there are two major cases in our 3x3 toy example. In the first case, threads that do not calculate valid P elements, they still need to participate in loading valid input tile elements. For example, during phase 0 of block 11, thread 10 is supposed to calculate a non-existing P32, so it's not calculating any valid P element. But it still needs to participate in loading the input tile element N12. The second case is that threads that calculate valid P elements may attempt to load non-existing input tile elements when loading input tiles. So for example, in phase 0 of block 00, thread 10, which is assigned to calculate a valid P10, may attempt to load non-existing N30. So this really suggests that we need to be able to test different conditions for each thread when loading tile elements versus when performing inner product calculation and write to the output element. And this is exactly what we're going to do in our kernel design. This leads to the solution that we will be adopting into our kernel code. So when the thread is to load any input element, we will test if it is in the valid input range. If the index to be used is in the valid input range, then we will proceed to load the element. Otherwise, we do not do any loads, but we just write a 0 into the shared memory. The rationale is that for matrix multiplication and inner product calculation in particular, a 0 value will ensure that the multiply add step does not affect the final value of the output element. Obviously, this is an application-specific approach. Each different application will likely require a different default value into those tile elements that would have been loaded from invalid input elements. Then the condition that we'll be testing for loading input elements is different from the test for calculating output P element. So when we do the inner product and doing the write to the output array, we will still make sure that a thread does not calculate the output P element, will not be able. With our new strategy, we see that the tile that we'll be using in phase 1 by block 00, the shared memory locations that would have been occupied by non-existing M and N elements are now filled with 0 values. So when all the threads attempt to use these values in their inner product calculation step, we will not contaminate the output values. In terms of implementation, we can now look at the boundary condition checking for loading input M tile. So we see that the index that we're going to be using in two-dimensional notation will be M using rho for the Y index and P times tile width plus TX for the X dimension. And of course, when we actually load it, we will be linearizing these two indices into a one equivalent one-dimensional index. However, for testing, we should just take the y-index and the x-index and make sure that they're both in the valid range before we do the loading. So therefore, the condition that we should add in front of the load in the kernel code will be that the row should be less than width, and p times tile width plus tx should also be less than the width. If the condition is true, we load the m element. Otherwise, we load a 0. So this is what we would see in our final kernel code. Similarly, when we load the input n tile, we can see that the equivalent 2D index for loading the n element will be p times tile width plus ty for the y direction and col for the x direction. We will be linearizing this two-dimensional notation into an equivalent 1D linearized index for the code. However, when we test the condition, we should separately test the y direction and x direction and make sure that they're both within the valid range. If true, we load the n element. If not, we load 0. So this leads to the modified kernel code that we should have for a tiled matrix multiplication kernel that would correctly test the boundary check for loading tiles. And we see that in line 9 and line 10, we have the proper load condition testing before the load, and then if the condition fails, we will add load 0 element into the shared memory location. This is done properly for both m and n. When we calculate the inner product, we still use the original row and column testing to make sure that the thread is actually calculating a valid output element. So, but keep in mind that because we have 0 values into the shared memory location that would correspond to non-existing m and n elements, we don't need to test for those when we do the inner product calculation. And of course, before we write out to the p element, we should also test that both the row index and column index are within the valid range, just like what we had in the previous kernel. To summarize, we make 2 important observations. One is for each thread, the conditions for loading the n element, and calculating this and storing the output p elements are all different. So this allows each thread to play a different role when loading the m tile, loading the n tile, versus calculating and storing the output p element. The second observation is that with all these conditions being tested in the kernel, we do expect to have control divergence. However, we also expect that the effect of control divergence will be small for large matrices. This is because the conditions will fail only when the threads attempt to load input elements or compute output elements outside the valid range. And these should be the minority cases. And there's for large matrices, most of the threads should be executing in the region where all these conditions will be true. So we would see some level of control divergence, but that their effect should be small for large matrices. At this point, we have a tiled matrix multiplication kernel that can handle arbitrary dimensions of square matrices. However, in general, the matrix multiplication is defined in terms of rectangular matrices. That is, a J by K M matrix multiplied with a K by L N matrix will result in a J by L P matrix. So we would like to be able to extend our square matrix multiplication kernel into a general matrix multiplication kernel that can handle arbitrary rectangular matrices. And it turns out that we can do this fairly easily from our current kernel. So we just need to make a few changes to the kernel function. We need to replace the width argument by 3 arguments, j, k, and l. Whenever width was used to refer to the height of m or height of p in the original kernel, we replace it with j. And when the width is used to refer to the width of m and height of n, we replace it with k. And when the width is used to refer to the width of n or width of p, we replace it with l. With these fairly simple changes, now we have a general tiled matrix multiplication kernel that can handle arbitrary rectangular shaped matrices. And this gives us a general functionality in terms of real numbers or single precision floating point numbers. In order to complete the matrix multiplication implementation, we also need to have functions that will be able to handle double precision real numbers, complex numbers, and integer numbers of various sizes. But all those variations can be based on exactly the same kernel function structure, but replacing the types of matrices with appropriate data types that we would like to support. So now we have completed a journey going from a simple matrix multiplication kernel and adding tiling functionality, acting the corner condition or boundary condition checking to be able to extend its ability to handle arbitrary dimensions. And then with some simple changes, now we can handle arbitrary input shapes of rectangular matrices. So this completes that journey. And in many real applications, the developers need to go through exactly this type of journey to be able to have a real general implementation of the function that they need to support. This concludes lecture 4.5 of the GPU teaching kit. Thank you.